Good evening and welcome to the session. So today's session is on symmetry observations in Fourier transform. We'll discuss some wonderful things, wonderful observations in Fourier transform. So there are a lot of questions which can be dealt easily with the help of symmetries that we can observe in Fourier transform. So let's talk about them in detail. And one more important thing is whatever symmetries that we observe in Fourier transform, same symmetry observations we can make in discrete time Fourier transform, DFT, Fourier series, and all of them. There are 4 tools for frequency analysis. First one is continuous time Fourier series. Second one is continuous time Fourier transform. Third one is discrete time Fourier transform. Last one is DFT. Now all these 4 tools, similar observations, whatever observations we are going to do in this session, same observations or similar observations you will be seeing in all the remaining 3 tools as well. So one thing, whatever we are going to learn in this session will be helpful in other Fourier tools as well. Okay, right. So these are my subjects of expertise: communication systems and signals. So if you wish to ask me any doubts based on these subjects, you can contact me in this group. This is my Telegram. Right. So let us start with the session. So before starting the session, let me quickly give you the answers for the homework questions that I have given yesterday. So I have given 2 homework questions in yesterday's session. In yesterday's session, we have talked about differentiation and convolution property of Fourier transforms. So I have given questions based on that. Okay. So let me quickly give you the answers for it. So first question. So inverse Fourier transform of this if you want. So inverse Fourier transform of this is, let us look at it as 40 divided by 6 square plus omega square. Convolution with. So this one, let us look at it as 50 divided by 25 is 5 square plus omega square. So the Fourier transform that we are familiar with is e power minus a mod t Fourier transform is 2a by a square plus omega square. So if it is here a is 6, so 2a should be 12 here. So let us put 40 outside and divide with 12 and multiply with 12. So it becomes 12 divided by 6 square plus omega square. Convolution with 50. So if a is 5 here, a is 5, 2a should be 10. So 10 should be here. Put that 5 outside and let us write as 10 divided by 5 square plus omega square. Now we want to find the inverse Fourier transform of this one. Okay. Inverse Fourier transform of this one. So we have to do some small arrangements of constants so that it will be easy to do inverse Fourier transform. So 40 by 12 outside we can put it, and this 5 also we can put it outside. Now let us find the inverse Fourier transform of this one. If you find the inverse Fourier transform of this total thing, it is as good as finding inverse Fourier transform of this, inverse Fourier transform of this, and convolution becomes multiplication when you take inverse Fourier transform. So 12 divided by 6 square plus omega square inverse Fourier transform is e power minus, in place of a it is 6 mod t. Convolution becomes multiplication into e power. The inverse Fourier transform of this part is e power minus 5 mod t. So which is equal to, so here you can cancel that 4 here. So then it becomes 10 into 5 is 50 by 3 into e power minus 6 plus 5 is 11 mod t. Okay. Fine. So that is the answer. So I'm asking you to find the value of this function. So same concept you can use. You can find the inverse Fourier transform of this one. In inverse Fourier transform, this will be something like e power minus 10 mod t, and this will become e power minus 5 mod t. Correct? And if you, so similar to this problem. So the convolution doing directly convolution of these 2 terms is very difficult. So what you can do is you can take the help of inverse Fourier transform or convolution property of Fourier transform, so that you can make this problem look very easy. So let us do this also. Right. So this one, let's do this problem. I'll reduce the number of steps because of space constraint. So let me write it as 2 into 10 divided by 10 square plus omega square So basically there is 100 here. So 2 into 10, if it is there, outside it will be 5. 100 I'm dividing it as 20 into 5. Convolution with. So 200, how do we write this? So it is 5 square plus omega square. Here a is 5. In place of a we are having 5. So it should be 5, 2 into 5. 10 should be there here. Which means 20 outside. Let me write as into 20. So 20 into 5, let us put it outside, which is 100 again outside. So 100. So 100 into. So for this one, if you find inverse Fourier transform of this one, let us find the Fourier transform of inverse Fourier transform of this one. Once you find inverse Fourier transform and then Fourier transform, what happens? You'll get the same signal, right? What I'm trying to do is, I'm trying to find Fourier transform of inverse Fourier transform of this total. 100, I'm putting it outside. So Fourier transform of inverse Fourier transform of 2 into 10 divided by 10 square plus omega square, convolution with 2 into 5 divided by 5 square plus omega. See this one? Once you find inverse Fourier transform and then Fourier transform, inverse Fourier transform operations get cancelled. Finally, you'll get the same thing. So which means, sir, you'll get the same thing now. Are we going to get a? Well, if you are getting the same result, what is the point of doing it? Come on, you'll get the result in a different format. But the idea is same. So if you find inverse Fourier transform once and find Fourier transform again, that result is same as this result, but in a different format. Let's do that. So this is equal to 100 multiplied with Fourier transform of. So what is inverse Fourier transform of this part? It is e bar minus 10 mod t. The convolution becomes multiplication, and Fourier transform of this inverse Fourier transform of this part is e bar minus 5 mod t. See this one, now it has become multiplication. So it is 100 times. So this is e power minus 15 mod t. This total thing is e power minus 10 plus minus 5 is e power minus 15 mod t. Whose Fourier transform is, let's find the Fourier transform e power minus 15 mod t, which is 2 into 15 divided by 15 square plus omega square. So the answer is 15 to 30. 30 into 100 is 3000 divided by 15 square is 225 plus omega square. That is the result. See how easily we can find the result of this convolution operation directly. If you are using convolution integral formula in frequency domain, it is very tough to find the answer. Very, very tough. 10 minutes also is not sufficient. But with the help of convolution property of Fourier transform, we can find it very easily. Okay. So shall we move on to the next part? Today's topic, symmetry observations. Very, very important observations. Very important. Very powerful. So these observations will help you sometimes in understanding whether your answer is correct or not. Also sometimes it may not be able to 100% tell that whether your answer is correct or not, but if it is sometimes incorrect, then we can easily identify with the help of symmetries. How? We'll see in the further slides. So first let us learn the basic. So what are these symmetries? Let us understand it from the very basic level. Let's take x of t is the signal whose Fourier transform is x of omega. Okay. Now let me write the Fourier transform formula. X of omega is equal to integration of x of t into e power minus j omega t dt. Limits from minus infinity to plus. Look at this one. I'll just rearrange it a little bit. I'll write e power minus j omega t as cos omega t minus j sin omega t. Is that okay? E power jx can be written as cos x plus j sin x, right? Same way. In place of x, we are having minus omega t. Now let us rewrite it as integration x of t into cos omega t dt minus integration of x of t into sin omega t dt. See this one? Basic Fourier transform formula. I'm just changing it slightly just to observe the properties, observe symmetries. Okay. Now x of omega, let me write this again. One second, j is there, no? J I forgot. X of t cos omega t, x of t sin omega t, minus sin, and j. J part is also minus j term into x of t into sin omega t. Look at this one. Can I write it as real part of the signal? This Fourier transform, I'm just dividing into two parts. A real part of the Fourier transform, and this part I'm calling it as imaginary part of the Fourier transform. Is it okay? This is real or not? This total thing. If x of t is real, if x of t is real, x of t is real, cos omega t is real, and remaining apart from j, the remaining part, x of t is real, sin omega t is real. So integration of x of t into sin omega t is also real. Okay. So can we write this as x of omega as a real part of the Fourier transform minus j times imaginary part of the Fourier transform? Is that okay? So Fourier transform just dividing into two parts. So this is real part. This part is real part only if x of t is real. If x of t is real, if x of t is real, then real part of the Fourier transform. Then real part of the Fourier transform is integration of x of t into cos omega t dt. And imaginary part of the Fourier transform is right. Sir, if x of t is not real also this will happen? No. See, if x of t is not real, which means it is complex. If x of t is complex, complex multiplied with real is complex. If you integrate complex, it will become complex only. Why will it become real? Correct or not? Only if x of t is real, we can call this part as real part and this part as imaginary part. If x of t is not real, if x of t is not real, then this is complex. This is also complex. Which means this will have a real part and imaginary part. This also will have real part and imaginary part. Only if x of t is real, only then this is valid. This we can call it as real part and this we can call it as imaginary part. Okay. If x of t is complex, then this will become complex, this will become complex. The total thing finally can be divided into real part and imaginary part, but that will become complicated. That is not as simple as this. Okay, I hope you're following. Now let's understand this. Can you replace omega with minus omega? If you replace omega with minus omega on both sides, here if you replace omega with minus omega, it becomes cos of minus omega t, which is also cos omega t. Correct or not? Cos of minus omega t same as cos omega t because cos is even function. Is that okay? Right. Next, replace omega with minus omega in this imaginary part also. What happens now? Integration from minus infinity to plus infinity, x of t into sine of minus omega t is minus sine omega t. Why? Because sine function is an odd function. Right? I hope you are understanding this. I believe this it is clear till this point. If there is any confusion, just let me know. Right. From these observations, compare these two and compare these two. From that relation, what can you say? This equation and this equation are same. So real part of omega, real part of omega, imagine x real part of minus omega, both are same, it seems. So we can understand that xr of omega is same as xr of minus omega. What does that say? So this is even function. Can we say that? Can we say that? This real part of the Fourier transform, this real part of the Fourier transform is also even, it seems. The real part of the Fourier transform is also even, it seems, because xr of omega and xr of minus omega both are same. That is the definition of even function. Right? Next, see this one. What is the relation here? Xi of omega and xi of minus omega is having a minus sign extra. So xi of minus omega is same as minus sign applied to this, which means minus xi of omega or minus xi of minus. See this one? Is this the definition of odd function? So imaginary part is odd, real part is even. See this one? X of omega, this is even function. Real part of the Fourier transform is even function and imaginary part of the Fourier transform is odd function only when x of t is real. Only when x of t is real, this happens. If x of t is complex, these things cannot happen, need not happen, right? So if x of t is real signal, then real part of the Fourier transform is even and imaginary part of the Fourier transform is odd. Together, what can we call it? What kind of symmetry can we call it? Okay, we have observed symmetries. If x of t is real, what is observation? Fourier transform x of omega. If you take the real part of the Fourier transform, real part of the Fourier transform is even symmetric, and imaginary part of the Fourier transform is odd symmetric. Together, if real part is even and imaginary part is odd, we can say the Fourier transform is conjugate even symmetry. It is conjugate even symmetry. For complex signals, we define something called conjugate even symmetry. Fourier transform, is it complex or not? See, Fourier transform is complex. Sometimes it might be real also, but when x of t is real, Fourier transform will be definitely complex. If x of t is just real without any extra symmetry, if x of t is just real, definitely Fourier transform will be complex. That j term also will be there. When j term is there, for the total function, for that complex function, we have two types of symmetries. One is conjugate even symmetry and the other one is conjugate odd symmetry. Only for real functions we define even symmetry and odd symmetry. So this complex Fourier transform has real part and imaginary part, which are both real signals. This is real signal, this is real signal. Two real signals combined with a j factor, we call it as complex signal. So these two real signals are having even and odd symmetries. Together, we call it as conjugate even symmetry. Again, conjugate even symmetry means for complex signal, we define this conjugate even symmetry. So for a complex signal, if the real part is even and if the imaginary part is odd, then together we call that complex signal as having conjugate even symmetry. Okay, I hope the first part is clear. How about the opposite? How about the opposite? Same concept, you can do the same derivation that I've done. Same analysis you can try it after the class. So x of omega, you just write the formula, inverse Fourier transform formula. Inverse Fourier transform formula you can write. Earlier x of t is given as real. Now x of omega they are saying it as real. So just take the inverse Fourier transform formula. X of t is equal to 1 by 2 pi integration of x of omega into e power j omega t dt. So you can just rewrite it as 1 by 2 pi integration from minus infinity to plus infinity x of omega into cos omega t dt plus 1 by 2 pi integration of x of omega into sin omega t dt, but there is a j factor extra here because e power j omega t can be written as cos omega t plus j sin omega t, right? So if x of omega is real, if this is real, if this is also real, cos is real, real into real is real, integration of real is real. So this total part is the real part, this total thing is real, and this total thing is also real apart from j. If you put aside j, this total thing is real. And one more thing, in this function, this is the time function, no? X of t, we can write as a real part of the signal, and this is imaginary part of the signal, right? In this signal, in this function, replace the variable with minus of that variable. So if you replace t with minus t in this function, you're getting the same function, which means this real part of the function is even, and similarly replace t with minus t here, you're getting a minus sign extra, which means it's a odd function. Same analysis that I've done in the previous slide, I'm just doing it quickly. Same procedure, exactly same thing. So you can observe that the real part is even symmetric and imaginary part is odd symmetric, which means together we call it as conjugate even symmetry. What is conjugate even symmetry? X of t is conjugate even symmetry. Okay. I hope it is clear till this point. Similarly, how about this? If x of t is purely imaginary, what happens then? Same basics, let us analyze quickly. If x of t is purely imaginary, we can comment something about the Fourier transform. So let's write the formula for Fourier transform here, and just to minimize the time, I'm just writing it directly. E power j omega t minus j omega t. I'm just expanding it and writing. Same expansion that I've done in the previous slides. Now this is purely imaginary. Purely imaginary means j times some real function. Correct? Imaginary function means it is j times some real function. J times real function is imaginary function. Correct? Purely imaginary means it's real function multiplied with some j factor. That kind of function. I hope you follow. So in that function, purely imaginary means if you put the j factor aside, the remaining part is purely real only. Correct? So this is purely imaginary. This is imaginary. It means something like jt kind of function. If you remove that j, it is a real function. Jt square, j sin t, something like that. So this is real, but with j, it is purely imaginary. So this is imaginary. Imaginary multiplied with cos is imaginary. After integration also, it will become imaginary because in that imaginary function, put that j outside the integration, and remaining thing will be real. With the j, it will become imaginary. So this total thing also will be imaginary part. Correct? This becomes imaginary part. How about this one? This is also imaginary. Imaginary means there is a j term extra. That j term with this j term, j into j is -1. So j will vanish in this term. So in this term, j with j real term will be there. That j and this j multiplied, it will vanish. J term will vanish. Finally, only real function will remain. Real into real is real. Integration of real will be real. So this total term will become real part. Correct? And if you observe carefully, we know since cos is there, only this part. This is real part of the this is imaginary part of omega, and this becomes a real part of the Fourier transform. This is real part of the Fourier transform. Okay. This is real part of the Fourier transform. Now, if you replace omega with minus omega in this function, then cos of minus omega t is cos omega t only. If you replace omega with minus omega, you are getting exactly same function, which means this is even symmetric. Similarly, if you replace omega with minus omega in this real part, if you replace omega with minus omega, sine of minus omega t is minus sine omega t, which means minus extra you are getting out of this function. XR of omega is not same as XR of minus omega. XR of minus omega and XR of omega are having a minus sign extra, which means this is a odd function. See, real part is odd, a real part is odd, and imaginary part is even. What do we call that? If real part is even and imaginary part is odd, we call it as conjugate even symmetry. The opposite of it is conjugate odd symmetry. If real part is odd and imaginary part is even, we call it as conjugate odd symmetry. Okay, I hope it is clear to this point. Same stuff again, the reverse. You can observe that if x of t is real, x of omega is conjugate even symmetry. Correct? If x of omega is real, x of t is conjugate even symmetry. Why is that happening? Why is that happening? In time domain, if it is real, in frequency domain, it is conjugate even symmetry. Similarly, in frequency domain, it is real. In time domain, it will be conjugate even symmetry. So, because Fourier transform satisfies duality property, whatever observation you make in one direction from time to frequency, same observations you can make from frequency to time also. So, and in a similar manner, if x of t is purely imaginary, we know x of omega, this implies x of omega is conjugate odd symmetry. In a similar manner, can you guess what happens here? Can you tell me what happens here? X of omega is purely imaginary means, what can you say about x of t? Using the information about x of omega, we can comment about x of t. What can we comment about x of t? X of t is a conjugate odd symmetry. In one domain, if the signal is purely imaginary, in the other domain it is conjugate odd symmetry. In one domain, if the signal is real, in the other domain it is conjugate even symmetry. I'll just summarize what we have discussed till now. X of t Fourier transform is x of omega. If in time domain it is real, infrequent when it is conjugate even symmetric. Similarly, if it is real or if it is conjugate even symmetric in one domain, in the other domain it will be real. Similarly, in one domain if it is imaginary or purely imaginary, in the other domain it will be conjugate odd symmetric. Or if you observe that in one domain it is having conjugate odd symmetry, it means that in the other domain it will be purely imaginary. Is that okay? Okay. If you want, I'll just give you some examples. Let me take a real signal. For example, e bar minus 3t Fourier transform is 1 by 3 plus j omega. See this one? Is this real signal or not? Yes. How about this one? Is this having conjugate even symmetry or not? This is definitely having conjugate even symmetry. Conjugate even symmetry definition I'll tell you mathematically also. X of omega is same as x conjugate of minus omega. So apply conjugate to this, then j becomes minus j. Replace omega with minus omega, replace omega with minus omega, and then apply conjugate. You should get the same function as the original function. Replace j with minus j and replace omega with minus omega, you're getting the same function, which means this is conjugate even symmetry. Sometimes when we do problems, just try to observe these things, if these things are happening or not. Sometimes we can find out our mistakes with the help of these properties also. Not always, but sometimes. Next, how about this one? E power j omega t. Fourier transform as e bar j omega naught t. It is 2 pi into del of omega minus omega naught. That is the Fourier transform of this one. See this one? Is this having conjugate even symmetry or this is a conjugate even symmetric signal? If you want, you can apply this basic, or you can divide this into real part and imaginary part and see if real part is even and imaginary part is odd. See this one? So this function, replace t is a variable here, replace t with minus t and replace j with minus t. You're getting exactly the same function. So it is having conjugate even symmetry. Or you can also write as cos omega naught t plus j sin omega naught t. Real part is cos, which is even. Imaginary part is sin, which is odd. So if it is conjugate even symmetric, is this real function or not? Just simple. There is no j factor here, so it is real. See this one, it is being satisfied. Okay. Similarly, imaginary function. Imaginary function means what? If you just multiply with j with this, on the other side also j gets multiplied. If you multiply a conjugate even symmetric function with the j, what happens? It will become conjugate odd symmetric. Correct or not? Let's say, let me take signal x of t, xr of t plus j times x imaginary part of t. If you multiply some signal with j, what happens? It becomes x, real part will become imaginary part, and j into j becomes minus 1. When you multiply any signal with j, what happens? Real part becomes imaginary part and imaginary part will become real. So if x of t has having the conjugate even symmetry, which means this is even and this will be odd. Now, yes, this is again even only and this is odd only, but the real part has become odd and imaginary part has become even because of multiplication with j. So if x of t is purely imaginary, which means take the real signal multiplied with j. If it is purely imaginary, then it will be having conjugate odd symmetry. Real part is odd and imaginary part is even. Okay. Similarly, conjugate odd symmetry also we can understand. In every Fourier transform that you do, in every Fourier transform problem that you do, you can observe these properties. Let's move further. Let's observe few more things. This is very, very important. The next 4 observations I'm going to make, beautiful observations. They are going to be very helpful. And these observations that we make in Fourier transform, in CTFT, continuous time Fourier transform, they are applicable for continuous time Fourier series, DTFT, and DFT also. So x of t, it is given as real and even. x of t is real means, what is the definition of real? If you take conjugate of the signal also, it should be exactly same as the resonance signal. And even symmetric means if you replace the variable with minus sign, you'll get the exact same function. If you replace the variable with minus of the variable also, still you'll get the same function. Only then we call it as having even symmetry. So it is real, it is even symmetry. So these are the conditions satisfied by the time domain signal. Next. So they're asking us to tell what is your observation on Fourier transform. If some information is given about x of t, if you have observed few things about x of t, in the previous slides we have observed about only if x of t is real or imaginary, or only those two things we are considering. Now we are seeing if x of t is having some symmetry also. We are adding one more dimension here. If x of t is having some kind of symmetry, then what is the observation of Fourier transform? You want to comment about x of omega, right? So since we want to comment about x of omega, let's write the formula for x of omega, which is integration of x of t into e power minus j omega t dt. So e power minus j omega t dt, I'll write as cos omega t minus j sin omega t. I'll write it same as what I've written in the previous slides. Okay. Since x of t is real, x of t is real, x of t is real, and it is also even. It is also even, and here also it is real and it is also even. So this total thing, since this is real into real is real, this total part is real, this total part is real, but multiplied with j, along with j, this total part is imaginary part. So this I'm calling it as real part of the Fourier transform, and this I'm calling it as imaginary part of the Fourier transform. Imaginary part of the Fourier transform. Okay. Now let's observe what is happening here. Say x of t is even, no? But the sin omega t is odd. X of t is even and sin omega t is odd. When you multiply even with odd, what is the resultant signal? Even into odd is odd, right? When you multiply an even function with odd function, the result is odd function. But when you integrate an odd function, what is the result? What is the result of integration of an odd function? What is the result of integration of an odd function? What is the result of integration of odd function? Anyone? Zero, right? Any odd function, take a signum function, integrate, it becomes zero. Any odd function, if you integrate, it becomes zero. So imaginary part is becoming zero. Is that okay? Imaginary part is becoming zero. Now, let's observe a few things about real part of the function. So real part of the function we know. Real part of, in the real function, if you substitute omega with minus omega, if you substitute omega with minus omega, what are we getting? If you replace omega with minus omega, cos of minus is plus cos omega, which means we'll get exactly same function. So in this real part, if you replace omega with minus omega, still you are getting the same function. So xr of minus omega is same as xr of omega, which means xr of omega is even as well. What can you say now? X of omega is only real part of omega plus j times imaginary part is 0. And this real part of the Fourier transform is also even symmetric. The real part is also even symmetric. So what can we comment about x of omega? X of omega is also real because only real part is existing, and it is also having even symmetry. Beautiful observation we made. So if x of t is real and even symmetric, then x of omega is also real and even symmetric. Easy to remember also. Whatever symmetry x of t is having here, real and even, same symmetry x of omega is also having. Is that okay? Fine. So let's move ahead. What if x of t is imaginary and even symmetric? Let's write the Fourier transform formula. X of omega is equal to integration of x of t into cos omega t dt minus j times integration of same analysis that we have done in the previous slide. Right. So what is given about x of t? X of t is, from this information we will have to comment about x of omega. Okay. So what is given about x of t is x of t is imaginary. Imaginary means if you apply conjugate for it, you'll get a minus sign extra outside. Or original signal, and if you apply conjugate, those signals are not same. They are same if you apply minus sign extra. And it is having even symmetry, which means x of t and x of minus t both are same in the function. In the variable, if you replace the variable with minus of the variable, you'll get the same function itself. That is what is the definition of even symmetry. Now this is imaginary and even, and this is also imaginary and even. Okay, now this is even, but this is odd. No, this is odd symmetry, this is even symmetry. Even function into odd function is odd function. X of t into sine omega naught, the result is an odd function, and integration of odd function is, the integration of odd function is what? 0. We have discussed that in the previous slide also. So only this part remains, only this part remains. Okay, only this part remains. But x of t is also even. Even into even is even. So this total function will be even because this is some function of omega. If you replace omega with minus omega, you're getting the exact same function. It means this is even symmetry. This is even symmetry. Very good. But since x of t is imaginary, if you put a j outside, then this total term also will become purely imaginary. So this is imaginary term because x of t is imaginary. Second term, this term is vanishing. If at all, if this term is existing, since x of t is imaginary, which means there is a j factor, j into j becomes minus 1, which becomes real. So this becomes the real part and this becomes the imaginary part. So this is imaginary part. So this is imaginary and it is also even. Why it is even? Because if you replace omega with minus omega, so this total thing is a function of omega. If you replace omega with minus omega, you are getting exactly the same function. Hence, it is a even symmetric function. Whereas this part is becoming 0 because x of t is given as even symmetric and sin omega t is odd symmetric. Even into odd is odd. Integration of odd function is 0. That's all. Okay, easy to remember. So what about x of omega now? X of omega is also imaginary and x of omega is also even symmetry. Whenever you're talking about even symmetry for x of t, same even symmetry is carried to Fourier transform also. And whenever x of t is even symmetric, if x of t is real, x of omega is also real. If x of t is imaginary, x of omega is also imaginary. Okay. Okay. So for you, I'll give you one example. E bar minus a mod t. See this one, is it even symmetric or not? It is an even symmetric function. Fourier transform is 2a by a square plus omega square. So if you plot this, this is also a symmetric function. This is also even symmetric function. So this is real and even. This is also real and even. Correct? Same example. So instead of e power minus a mod t, you take it as j times e power minus a mod. Then it becomes imaginary and even. On the other side also j should be multiplied because of linearity property. Same example, using same example, you can also understand this property. So if you put a j here, then the same j will be here also. So then it will become purely imaginary term, imaginary and even. Then this also becomes imaginary and even. Correct? So that is the example. Next, more. So let's talk about if x of t is imaginary and odd symmetric, what happens? So if x of t is imaginary and odd symmetric, we have to comment about x of omega. We have to comment about x of omega. Let's comment about x of omega by writing the formula for Fourier transform. X of omega formula is integration of x of t into e power minus j omega t Instead of e power minus j omega t, I'm writing it as cos omega t minus j sin omega t. Okay, right. Now what is given about x of t? It is given as imaginary. If x of t is imaginary, this total thing will become imaginary part, and it is also having odd symmetry. Here also x of t is given as imaginary and odd. See this one, this will become, this term, will it become imaginary term or not? Because cos is real, x of t is imaginary, so imaginary into real is imaginary only. So this total term becomes imaginary term. And how about this term? X of t is imaginary, which means there is a j factor, j into j becomes minus 1. 2 j's, it will become real. So this total term will become a real term. Okay, next. If x of t is odd, if x of t is odd, this is odd, this is even. How about even into odd? It is also odd. Even into odd is odd. Integration of odd, integration of odd becomes 0. So if it is 0, whether it is imaginary or real, it should not matter for us. Next one. So x of t is given as odd symmetric. Sine is also odd symmetric. Odd into odd. Two odd functions, if you multiply, it will become even function. Integration of even function need not be 0. Okay, right. So this is a function of omega, right? This is a function of omega. Replace omega with minus omega. If you replace omega with minus omega, minus we can put it outside, because sine of minus omega t is minus sine omega t. Minus is coming outside. In any function, if you replace the variable with minus of the variable, if minus is coming outside, then it is a odd symmetric function. So this is vanishing. Only this exists, but this whatever is existing is real, and it is also odd. So the comment about x of omega is, if x of t is odd, mind this, if x of t is odd, x of omega is also odd. If x of t is even, x of omega is also even. Perfect. But here, whenever x of t is odd symmetric, the other part is becoming reversed. So if x of t is imaginary, x of omega is becoming real. X of omega is becoming real. Okay. Whereas when x of t is real, x of omega is also real. Sorry, when it is even symmetric, then if x of t was real, x of omega is also real. When x of t is even, if x of t is imaginary, x of omega is also imaginary. But when x of t is having odd symmetry, whenever it is odd symmetry, the other part of the observation is becoming opposite. If it is imaginary in time domain, it is real in frequency domain whenever we are having odd symmetry. Let's observe the last one more observation. So let's observe one more thing. If x of t is imaginary and odd. Okay. We have talked about real and odd, right? Let's talk about imaginary. If x of t is imaginary and odd, what happens? Same basic, same understanding. X of omega, let me write the formula for it. Artha, you're asking something? Are you talking about this one? Are you talking about this one? Can you respond quickly? How it is odd, you're asking, right? So x of omega, in this case, x of omega is j times integration of x of t into sine omega t. Because x of t is imaginary and odd. Only under the condition that x of t is imaginary and odd, what happens? When x of t is imaginary or not, this term gets cancelled. Only this term remains. Though j is there, it's not imaginary term, because x of t is imaginary. That imaginary with j will become real. Okay. Now x of omega Fourier transform formula basically is this, but because of symmetry in x of t, because of odd symmetry in x of t, this term is vanishing. Now what about x of minus omega? See, whenever they are talking about even or odd symmetry, Even in odd symmetry is just a comparison between x of omega and x of minus omega. See this one, x of omega and x of minus omega, if you compare, if they are same, that means it is even symmetry, right? And similarly, x of omega and x of minus omega, if you compare, and if they are exactly having a minus sign extra, then it means they are having odd symmetry. So take x of minus omega, replace omega with minus omega, replace omega with minus omega everywhere. So sine of minus omega t becomes minus sine omega t, minus sine omega t, minus, I'm putting it outside. So x of omega and x of minus omega, if you compare, are they same? No. Are they same as odds? Are they same with exact extra minus sign extra? Are they satisfying this relation? Yes, they are satisfying. So that's why I said it is odd. Previously also we have observed similar things, right? So I thought you will be able to understand. That's why I did not explain more detail. But that is the idea. So this is some function of omega. In any function, replace the variable with minus of the variable. If you are able to pull the minus outside, minus sign outside completely, then it means it is having odd symmetry. See this one, x of minus omega. In that, if you are able to pull the minus sign outside, then it becomes minus x of omega. Then it is having odd symmetry. Okay, right. One more last thing, and then we'll summarize everything. So I'll just quickly write the formula, which we were writing earlier also. The formula for Fourier transform. So when x of t is given as imaginary and odd, what is the understanding of x of omega? What is the observation in x of omega? So let's quickly understand this one. This is the last symmetry observation. So it is given that x of t is imaginary. Second, what did we observe previously? X of t is imaginary and not symmetric, right? So we have to talk about real and even symmetry. My mistake. Imaginary and odd we have already talked about. So let's talk about real and odd symmetry. Let us talk about only x of t. So x of t is real and it is also odd. X of t is real and it is also odd. First, let us take the real thing. So if x of t is real, this total term will become real, correct or not? If x of t is real, real into real is real, integration of real will be real. And how about this one? Let us talk about the real thing here. X of t is real, sine omega t is also real, real into real is real, integration of real is real. Real, but the j factor is there. No? I missed the j factor. X of t into integration of x of t in d power minus j omega t, if you expand, it becomes cos omega t minus j times sine omega t. So x of t is real, this is also real, the result is also real, but j factor is there. Because of j factor, this becomes imaginary. Is that okay? This term becomes imaginary term, this term becomes real term, because x of t is given as real. Next, let us apply the second thing. If x of t is odd symmetric, cos omega t is even symmetric, we know that. Odd into even is odd, correct? So this result, inside this integration, whatever we are having, the total signal x of t into cos omega t is an odd function, because individually one is odd and another one is even. So result signal is an odd function. Integration of odd function is 0. From the information that x of t is odd symmetric, we can say that the real part is becoming 0. So how about the imaginary part? X of t is odd, sine omega naught t is also odd. Whenever you multiply two odd functions, the result is an even function. When you integrate even function, it need not be 0. And how about the symmetry? This is not 0, that much we know. How about the symmetry? Any symmetry here? In this total function, what is the variable? After integration, t will vanish, only omega will be the variable. So finally, x of omega here, let me write it as x of omega is equal to j times integration of x of t into sine omega t dt. You can write the formula for Fourier transform in this way only if x of t is real and odd. Okay, if x of t is odd, we can write it. Okay, now see this one. If you take x of minus omega, even symmetry or odd symmetry, both of them you can observe very easily. If you want a function, if you want to observe if a function is symmetric, having some symmetry or not, replace omega with minus omega. That's it. After replacing omega with minus omega, look at that function. Look at that resultant function. So sine of minus omega t is minus sine omega t, minus sine outside. So if you compare these two, what is happening? X of omega is same as x of minus omega. What is this definition? It is the definition of odd symmetry. So this part is a function of omega. If you replace omega with minus omega, minus is coming outside, which means it's an odd function. I've explained that in detail here. So what is observation finally? If x of t is real and odd, whenever x of t is odd, x of omega is also odd. Whatever symmetry is there in time domain, same symmetry is there in frequency domain also. Yes, okay, this one, yeah, this also will be there. Yeah, my mistake here. So here one more minus n, it will become plus. Correct, Artha. Thank you. So this minus n in Fourier transform, this part will become 0. This part, if you take it, this minus n also will be there. This minus n will be there. Here also I missed the minus. So it will become plus. Right. Correct. Is that okay now? So if x of t is odd, x of omega is also odd. Whatever symmetry is there in time domain, same symmetry is carry forward in frequency domain also. So if x of t is real, in time domain if it is real, in frequency domain it is imaginary. Okay. So let us summarize everything. If there is any doubt, you can ask me. I'll explain once again if there is any confusion or any doubt. I'm summarizing everything here. Whatever we've discussed in today's session, or whatever the possible symmetries are there, whatever symmetry observations are there, that I have put it in one place. If x of t is real, if x of t is real, we have discussed this. If x of t is real, x of omega is conjugate even symmetry. Correct? We have observed that all. In one domain, if it is real, see this one in frequency domain also if it is real, frequency domain also if it is real, in time domain it will be conjugate even symmetry. Right? In one domain if it is real, in the other domain it is conjugate even symmetry. Whether it is real in time domain or in frequency domain, if it is real in one domain, in the other domain it is conjugate even symmetry. Similarly, if it is imaginary in one domain, if it is imaginary in one domain, in the other domain it is conjugate odd symmetry. See this one, if it is imaginary in one domain, in the other domain it is conjugate odd symmetry. Imaginary in frequency domain, conjugate odd symmetry in time domain. Very simple observation. They are very easy to remember also because there is a dual relation between Fourier transform pairs. The same observations we can make in this CTFS, continuous time Fourier series, DFT and DTFT. Same observations, right? And few more important observations that we have made in today's session. Real and even. If it is real and even, it is real and even. If it is real and odd, it is imaginary and odd. If it is real and odd, it is imaginary and odd. See this one? Even in time domain, even in frequency domain. Odd in time domain, odd in frequency domain. Even in time domain, even in time domain. Odd in time domain, odd in frequency. Symmetry is carry forward. Whatever symmetry we have in time domain, same symmetry is there in frequency domain also. But whether it is real or imaginary, that will change slightly whenever it is even symmetry. See this one? Whenever it is even symmetry. If it is real, it is real in frequency domain. If it is imaginary in time domain, it is imaginary in frequency domain. It is easy to remember whenever it is even. Real and even means in other domain also it is real and even. Whenever it is imaginary and even, then also it is imaginary and even in the other. Easy to remember. For odd case, whatever symmetry is there, same thing carry forwarded. But whenever you are having odd symmetry, the other part is reversing. If it is real in one domain, in the other domain it is imaginary. Similarly, if it is imaginary in one domain, it should be real in the other. So previous one should be real and even, not real and odd. Okay, what is it? Did I make any mistake? So odd means odd, real imaginary means it will become real. If it is imaginary and even, if it is real and odd, it will become imaginary and odd. Correct only, no? No mistake. Correct only. I believe you are confused with this part. So there is a minus sign here. If there is a minus sign here, if you replace omega with minus omega here, sine of minus omega t, minus will come outside, minus into minus will become plus. So these two are not same, they are having a minus sign extra, which means it is having odd symmetry. I believe you are following. It is correct only, whatever I've written is correct. I hope you will not forget these things. Very easy to remember. Very simple things, only two things, real and imaginary. Same things are in frequency domains. And here also, even means it is even. Whatever symmetry you are having in time domain, same symmetry in the frequency. Whenever it is even, it is exactly same thing in frequency. But whenever it is odd, if it is real, it is becoming imaginary, and if it is imaginary, it is becoming real. So are you talking about this one? Can you respond quickly? Second last one. This one? Okay, good. Right. So if it is imaginary and even, right? So this is even. If this is even, x of t is even. Even into odd is odd. Integration of odd is becoming 0. Okay. Right. Next, x of t is imaginary. If x of t is imaginary, this total thing will become imaginary. That is fine. Now, what is the formula for x of omega? Let's write it. It is integration of x of t. No, are you not talking about this one? Cos omega t dt. Limits from minus infinity to plus infinity. Plus second part becomes 0. This happens only if x of t is imaginary and even. Imaginary and odd case. Okay. Fine, no issues. I'll talk about that case. So, but in this case, so if you observe, if you replace omega with minus omega, you'll get the same function. Hence, it is even symmetry. Imaginary and odd case. I think this one only should be this case only, right? Fine. There are only two cases. Only two imaginary cases. This is the first one. Other two are real cases. Two real cases and two imaginary cases. So I was talking about this. I think here there is no confusion. So if you replace omega with minus omega, you will get exactly the same thing because cos of minus is same. I'll talk about both the cases once again. Just listen carefully. Second case, this is the case. I think you are talking about this one only. First part is becoming 0. Second part is not 0. That is what we have written. So minus sign here. Now if you replace omega with minus omega, wherever omega is there, replace it with minus omega. Sine of minus omega t becomes minus sine omega t. That minus will come outside. Minus into minus will become plus. It should be real and even, you are saying. Why it is even? Why is it even? It is odd only, no? What is the relation between these two? What is the relation between? Are they same? Are they same? Tell me. Are they same? There is a minus sign extra, no? You have replaced omega with minus omega. When you replace omega with minus omega, what happens? A minus will come outside. So this minus sign will become plus sign because sine of minus omega t is minus sine omega t. So these two are not same. They're having an extra minus sign, which means it means it is having odd symmetry. It is odd only. Correct. Whatever I mentioned is perfectly correct. I believe now you got it. There might be some confusion for you. So just think about it once again. You'll get it. It is not real and even. It is real and odd only. Okay. Fine then. So that is the understanding of symmetries in Fourier transform. So any Fourier transform problem, you take it, you can observe these symmetries. Okay. So that's it on today's session. So before leaving, let me give you few questions and observe symmetries. Okay. Okay. U of t. What is the Fourier transform? Pi into del of omega plus 1 by j omega. I'll give you some Fourier transform. I'll write some Fourier transform formulas which are very important to remember. And in them, let us observe the symmetry relations. Two a by a square plus omega square. And one more formula is e power minus a t into u of t. Fourier transforms. Here a should be greater than 0. Otherwise, Fourier transform will not exist. So it is 1 by a plus j omega, where a is positive. And then what are the other transforms? Impulse function, it's very simple. Del of t Fourier transforms. Signum of t Fourier transform is 2 by j omega, correct? 2 by j omega. See, the j will vanish because, yes, j will definitely vanish because x of t is imaginary. Inside x of t there is a j term, and that j and with this j together it will become real. That is what we have written. Right. So these are the Fourier transforms I would suggest you to remember. The remaining transforms, all of them or most of them, we can get it using properties. See, that's what you're getting confused again. See, that j is there. We don't know exactly what is x of t. They said that x of t is imaginary, which means x of t is something like this, something like jt or jt square, something like that. Inside that function, if you write the function for it, exact function for it, inside that there is a j. If you substitute that function here, then that inside j with the external j, that will go. The j will vanish. This j with the j inside x of t together, j into j becomes j square, which will become minus 1. So that imaginary term, that j term will vanish because of a j term which is inside x of t. This j, if you don't write, then it will become imaginary. See here, this j is there. This term is not 0. So that's why we carry forward that j. Yes. Right. So these are the 5 Fourier transform I would suggest you to remember. Very easy. Del of t is very easy to remember. So this we frequently use. This also we frequently use. This also we frequently use. Signum function is one transform we don't use much, but that is also very important. Right. Let us observe them. Let us observe the symmetries here. U of t, is it real or not? Yes, it is real. Is it having any symmetry? Is it having any odd or even symmetry? No. It exists only for positive time. So there is no odd or even symmetry. So only real. So in Fourier transform, we know that it should be having conjugate even symmetry from our observations previously. Let's see if it is having conjugate even symmetry or not. So this is the real part. This is the real part, and this is the imaginary part. Is the real part is the real part even symmetry? Impulse function is even function, right? Impulse function is an even function. Next, 1 by omega. Is this an odd function? Yes, it is an odd function. Why is it an odd function? Replace omega with minus omega. Minus is coming outside. It is an odd function. Correct? Real part is even, imaginary part is odd, which means it is conjugate even symmetry. Whatever observations we made generically, you can observe for some specific signals also. Next, this one, it is even symmetric and it is also real. It is real and even. For a real and even signal, from our observations, we know that Fourier transform also should be real and even. Right? Very good. So is this real and even? Yes, this is real. There is no j term here. Hence it is real. Is it even symmetric? Yes, omega square term is there. If you replace omega with minus omega, you'll get the exact same function. Hence it is even symmetric. Next one. Is this real? Yes, it is real. There is no symmetry here because it exists only for positive term. So if it is real, here it should be conjugate even symmetry. Correct? Yes, this is conjugate even symmetry. So conjugate even symmetry can be looked at in two ways. By if you can write the complex function as real function plus j times imaginary function, then you can look at the even symmetry in real function and odd symmetry in imaginary part. Or the other way of doing it is, the definition of conjugate even symmetry is take the function, apply conjugate to that function, and apply replace omega variable with minus of that variable, then you'll get exactly original function. That function, take the function, apply conjugate, and then replace omega with minus omega, you should get the exact same function, then only it is having conjugate even symmetry. See this one? Replace omega with minus omega and j with minus j. Conjugate means replace j with minus j. Then you'll get exact same function. Next, del of t is even function. It's real and even. So this also is real. One means constant function, which is also even symmetric. It's a DC value kind of. It's a constant thing. Constant function is a even function. Next, signum of t. I believe you have imagined the signum function. This is how it looks like: 1 and minus 1. Signum function is odd function. It is also real and odd. It is real and odd. So for real and odd function, if it is odd symmetric in frequent time domain, it should be odd symmetric in frequency domain also. But if it is real in time domain, it should be imaginary in frequency. So if you want, you can cross check the previous slide. See this one? See this one? Imaginary and odd. It is real and odd. Or real and odd in time domain, imaginary and odd in frequency. See this one? Is this imaginary? Yes, because of j, it is imaginary. And because just omega power 1 means if you replace omega with minus omega, you get a minus sign extra, which means this is an odd function. Like this, you can verify the symmetries that we have observed in Fourier transforms in every Fourier transform problem that you are doing. And not only here, Fourier transform, you can also do the same symmetry observations in Fourier series, discrete time Fourier transform, and DFT also. All the Fourier truths. You can make same observations. Fine. So that's it from my side. So there are no questions are possible here. No numerical questions are possible. It's only just observations, right? So that's why I'm not giving you any homework in today's session. So that's it from my side in today's session. So I think tomorrow is the last session that I'm taking on Fourier transform. So I've covered many important concepts of Fourier transform. Most of the important concepts I've covered, but there is a few more things left to be covered. But with the time that I am given, so I've covered as much as I can cover. Right. So tomorrow's session will be a practice session. Among whatever topics I have discussed in the last 6 sessions, so I'll be discussing wonderful questions based on those concepts. You can think of it like a practice session or a testing session. So you can come to the class and whatever problem I give, I'll wait for a few minutes. You can try to solve it in 1 or 2 minutes, which will tell you how good you are in Fourier transforms. Okay. So if you want to test your expertise in Fourier transforms, you can attend tomorrow's session at 8 o'clock. Okay. So if you like the content of today's session, you can like the video. If you have not subscribed to the channel, you can subscribe. So that's it from my side, guys. Thank you. Take care. Good night.